calcium on the top. Heat it up. You're good to go. Just hope nobody tips it over.
Tipping it over, like if it was to short, that wouldn't really hurt it permanently, would it?
No, you just tip it back over and let it, separate by gravity again, and you'd be good to go. But this guy Don Sadoway, he's a real piece of work. I really got annoyed by his TED talk from long ago, where he said everything's wonderful and so on, and then he proposes using antimony. It's less abundant than lithium.
Yeah.
Doesn't make much sense.
Yeah, for sure. The other thing was the nominal voltage of like 1 or like 0.9. I can't imagine the manufacturing of a 1500 volt storage facility. It's like
a lot of interconnects.
Yeah.
Yeah, when they first put that thing out, they were talking about using magnesium and antimony. And then for a while they switched to lithium and antimony. So then it got even worse, because he started off saying, oh, we're going to get away from lithium. And then he's using lithium and antimony.
Yeah.
And then finally they switched to calcium, which is, at least somewhat sensible. All right, it's time to begin. So let's start and see what we can get done today. Yeah, so we were talking about solid-state diffusion in electrode particles, and we got to this page where there's some really bizarre formulas here with a lot of variables that aren't explained. And I want to explain what these variables are to you, so that when we take a look at graphs, we can understand what's being plotted versus what. So I want to describe what this quantity x as a function of z and tau is, what is q, what is t, what is tau, the Greek tau that you see where my mouse is circling, and these alpha, what are these things? So I'm going to switch over to my document camera so I can describe that. All right, I believe you should see my document camera now. Is it true?
Yep.
All right, so let's talk about these things. So first I want to talk about r squared over d. So r is the diameter of a spherical particle, the diameter of a cylindrical rod, or the total thickness of a plane of a slab that the lithium's intercalating into. And d is the diffusion constant. So if r has dimensions of centimeters and d has some dimensions of centimeters squared per second, this r squared over d has units of seconds. And this is the characteristic diffusion time. So what it means is, if you work out r squared over d for the particle that you're talking about, this will be approximately the time it takes within a couple factors of 2 or 3 for the lithium to diffuse virtually fully from the surface into the bulk. And when you're removing the lithium, the same is true, from within the bulk to outside. So this is your characteristic diffusion time. So then what matters when you're operating a lithium-ion cell, where you're trying to intercalate lithium into or out of these electrode particles, is the time that you're expecting the lithium to go in and out, that's t, compared to this characteristic diffusion time. That ratio is called Q. So T is the time to fully discharge if the electrode is completely filled. And for everybody that's in my laboratory and Overback's laboratory and Lucas Swan's laboratory, if you talk about working out a C/10 rate for an electrode that you've worked on, then this big T is 10 hours. If you are going to charge and discharge your cell at C/3, nominal C/3, then big T is 3. Okay, so if big T is very large compared to the diffusion time, that will give the lithium plenty of time to diffuse into the particles, and you'll be able to get pretty much full capacity from the electrode. But if big T is much smaller than R²/D, then you will find that you can't get all the lithium into the particle because you're just not giving it enough time to diffuse inside. So Q equals 1 is the crossover point, where if you have Q greater than 1, everything's fine. You can pretty much get the capacity you expect. But if Q is much less than 1, you'll get reduced capacity. Okay, so then there's this quantity tau. So what is tau? Tau is the ratio of the actual clock time to this time that you're expecting it to take for the electrode to fill. So this, as at any particular time, this gives you the fractional capacity. For example, if big T is 3 hours, you're doing C/3, and if you're at 1 hour, well, then the electrode is 1/3 filled with lithium. It may not be uniformly distributed in the particles because it's diffusing around, but still, you've added 1/3 of what you could. So this tau is the fractional capacity. Okay, now there's a sort of inconvenient feature of Atlung's paper. He uses the symbol X for 2 different things, but one of them is a small x and one of them is a capital X. And on my page, it's hard to distinguish a small x from a capital X, so I've labeled them big X and small x. So the normalized coordinate within the particle is Z, and that's the ratio of X to R. X varies between 0 and R. R is the diameter of the sphere or the diameter of the cylinder or whatever. So Z varies between 0 and 1. X, big X, is the lithium concentration. So that would be like Li subscript X TiS2. This varies between 0 and 1. And X star is the surface concentration of the lithium. So it means if you look at the surface of the particle, what fraction of the available sites are filled? 1 means they're all filled. 0 means none of them are filled. And then the lithium content at any point in the particle is a function of the position in the particle. So for a sphere, which is spherically symmetrical, there's only one position variable that matters, and that's how far you are from the center of the sphere, and that's Z. Same for the cylinder. It only depends on how far you are from the center. And for the slab, it only depends how far you are from the midpoint of the slab. And then this concentration depends on the time. And he plots the time in terms of the fractional time it should take to discharge the whole electrode. So this is what the variables in his treatment mean. And they're all very simple. You just have to remember what they are. And I'll try to remind you as we go through this next few slides, okay? Now, when we go back to the PowerPoint, you're going to see in his equation a summation over the subscript I. And in the summation, there's a bunch of alphas there. And for spheres, I've written down what those alphas are. And the alphas are given in the paper. They're just not on the same page that shows up on the discussion that I'm talking about. So does anyone have any questions about these variables here? Okay, the most important one to keep in mind all the time is Q. You know, Q is important to keep in mind. So we'll go back to the PowerPoint. Okay, so here we are. And this equation 8 here gives you an expression for the lithium content, X, as a function of tau and Z, and how it depends on Q. And then here's the summation. You can see these alphas. So you have to go to the table and figure out what these alphas are. And then he says we're primarily interested in the surface concentration, X star, which is obtained for Z equals 1. Well, that's right, because remember Z is X over R. If X is equal to R at the surface, then Z is equal to 1. And then you get a formula shown here as equation 9, where there's some funny constants A and B, and these alphas again, and the A and B are shown here, okay? So you can use these equations to probe what happens when you are delivering lithium to the surface of a particle at various current densities and see what happens. So I did that for a number of situations that we'll talk about. You'll do that in your homework 6 as well. All right, so what we're working on here is plotting the local value of the lithium occupation, X. Okay, so that in Atlong's paper, that's big X. Here I'm just calling it small x. And this is for a slab. Okay, so this is the fractional position in this slab-like particle. So this would be the right surface of the slab over at 1, and the left surface of the slab at -1. And this is the coordinate Z, right? Okay, so then what happens here? What we're plotting is X, that's what these curves are, as a function of position at various values of little t over big T. So what does this mean? It means that if little t over big T is equal to 0.1, that means you've spent 1/10 of the time you expect it should take for your cell to be fully discharged. So if that were C over 10 discharge, then this would be at 1 hour you'd be looking. And you can see the way the lithium concentration is larger at the surface and smaller in the middle. And this gradient is here so that the lithium can diffuse from the surface to the center. And then as time proceeds, you start filling up the particle. You continue, this is always the same gradient here because it's the same current density being applied at the surface. So you have to have the same flow of lithium from surface to the center. So now in the second graph of this panel, now we have Q equals 1. The bottom panel was Q equals 5. Q equals 5 means the time that we're trying to add the lithium to the particle is 5 times greater than the characteristic diffusion time. So here's our Q equals T over R squared over D. And then with Q equals 1, now you can see the issue that you get into. The surface concentration becomes fully filled before the center is fully filled. And what this means is there's a large fraction of capacity that you don't get. You just don't fill the interior of the slab all the way. And once the surface concentration reaches 1, you can't put any more lithium in. And that means the cell voltage would drop like a stone. And then if you go to Q equals 0.02, now you can see that the concentration gradients in the particle are incredibly steep. And you reach a filled surface at only about 1/6 of the total time that you expect for the discharge to take. Okay. And if you look closely at this graph, you'll see there's some little oscillations in it. And this is because in this calculation, I only use the first 3 values of alpha in the summation in the formula. And people in my group that have been associated with diffusion studies know that to eliminate these oscillations, you need to include quite a few terms in the expression for X, big X. But for the purposes of our class, we'll only include the first 3 terms just because it gets too cumbersome to put in more. Okay, so any questions about this graph? This is a very, very nice graph, you know, really makes a nice picture of what's going on for the various times during the discharge.
Jeff, for the high rate charge test, like 1C or 2C, 3C, what is that value corresponding to Q normally for our punch cells when we do this fast charge and discharge?
Yeah, I think the value of Q in that case is somewhere around probably 2 or 3. We're not in the limit of Q equals 0.2, that's for sure. Much of the limitations we have at those rates come from the electrolyte transport, not from the diffusion of the particles.
Okay, thank you.
Is there a commonly accepted Q value that will result in a small t over big T of 0.99? That's just like I know there is, but I'm asking I'm essentially asking what it is. Yeah.
I don't know the answer to that, but I would imagine it's something like Q equals 30 or something. It'd be a pretty big value of Q. That's a good question. Can get you guys to work that out in the homework. That's not so meant to discourage questions, by the way. Okay, so then, what do we have here? Okay, so here we're plotting the fraction of the sites filled at the surface. Okay, so what that is the surface concentration that you see here as a function of the fractional capacity that we had obtained. So at Q equals 5, the surface concentration is bigger than that you would expect in equilibrium. I mean, in equilibrium, the surface and the bulk would be the same. And when you get to the end of the discharge, the surface is full before the whole particle reaches full filling. And this intercept with the upper x-axis is about 0.93 something. It's exactly what we see in this graph. It takes 93% of the time you think it should take for the discharge. And then at Q equals 1, you can see the surface concentration becomes very different than the average composition in the particle, right? Like here at 0.6, the average composition is only about 0.3. So for people that are doing experiments like trying to measure a good differential capacity curve, this is why we go so slow when we're trying to measure good DQDV for DQDV analysis. You want every part of the particle to be at the same lithium content. You know, and if you're running at Q equals 1, the surface is at 0.6, the average is around 0.23, and you can see the huge range that you have, right? It goes all the way from about 0.15 up to 0.6. So you're never going to get anything that looks like an equilibrium set of data if you do the experiment so fast. And then finally, at Q equals 0.2, you see that the surface is full by the time the average is only at about 0.16, right? Okay, so any questions about this slide?
So, Jeff, quick question. So in order to model charging and discharging of a battery, typically we use this model, diffusion model, and then we assume a particle size distribution.
Well, I'll come to that in a few minutes. This is, we're still in sort of the baby steps here, okay? We're just learning about the basics of solid state diffusion where everything is the same particle size. The diffusion constant does not vary with the lithium content. This is all baby stuff, just to give you a feeling for what's important. You know, I'm a great believer that you need to have this, some kind of a foundation before you start talking about complicated stuff.
Got it.
When we have
okay, so here's, yeah, go ahead.
When we look at papers of rate maps, we normally see like when people increase the C rate from lower C rate to higher C rate, we see a capacity drop. Is this related to this, or it's because of the electrolyte, or related to some other factors?
It can be both, but definitely eventually you'll reach the rates where the diffusion into the particles becomes very problematic. Okay, so I have a question for all of you people. We'll see if you understand what's been going on here. So let's say we want to increase Q, right? We want to increase Q. We're going to talk about the same material, and we don't want to change the time that we're charging and discharging the cell. So let's say it's a C/3 rate. So we're not going to change big T, and we want to change Q. What do we have to do?
Change R?
Yeah, you change the particle size. So if you're in a situation where the limitation in your ability to charge or discharge fast is the particle size, you just make the particle smaller. And you'll find that high-rate lithium-ion cells have a smaller particle diameter for both the positive and the negative side particles. They'll be, instead of like 15 microns at the positive side, they'll be more like 5 if you really want to go fast. Okay, so then you can then calculate the impact of all of this on the voltage curve, because the surface concentration sets the voltage. So if you know X at the surface, you just put that value of X into our mean field expressions, for example, for the voltage curve, okay? So I picked one here that sort of mimics titanium disulfide, 2.5 volts equilibrium voltage, and then you've got a repulsive mean field interaction of ½ volt for X = 1, and then this entropy related term. We've seen all this before, okay? So in equilibrium, you'd follow this dash curve, right? But then when you start running at Q = 5, you get the blue curve. And then when you run at Q = 1, you get the green curve. And when you run at Q = 0.2, you get the red curve. And you can see how this impact of diffusion offsets the voltage downward. right? And to first order, it's a shift that affects the voltage curve everywhere evenly at sort of low rates. And then it just chops off the voltage curve at the high end. So you don't just come along straight and then die. It kills you off, at lower voltage early. So these type of calculations are really useful to do. They're really useful to be able to do because it gives you an estimate of what should happen to the voltage curve if you're in this solid state diffusion limit and you're just going too fast. Okay, any questions about that? All right, so you'll do examples like this in homework 6. Calculations like this in homework 6, sorry. And
Jeff?
yeah.
Sorry if I missed this because you were breaking up on my end for a few seconds, but where was the equation derived that links voltage to fractional capacity?
This equation here?
Yeah.
We did that earlier in our lattice gas models treatments in the course. So when we were talking about mean field theory long ago,
That's right.
We derived equations like this.
Yep. Thanks.
Yeah.
So that equation for voltage there, that's for random filling of sites, right? Does that change for if we're doing ordered filling, or does, if we change the rates here and we change Q, will that affect whether we have more ordered or random filling in the lattice gas model? Or are those two independent concepts?
No, they're not independent. It's a very good question. So, this is what I was saying before. If you end up with a large range of compositions in the particle, and you only have, let's say, an ordered phase around x equals a third, then some small fraction of the sample will be in the ordered state, and the rest of it will be in disordered states. So what that does is it smears out the features in the voltage curve, because at an ordered state you expect a drop in the voltage, and it smears out the features in the differential capacity. So for people that are used to looking at differential capacity of, things like lithium nickel oxide, high nickel materials, just run a cell at 1C rate and then look at the differential capacity curve, and you'll say, my God, where did all the features go? Because they'll all just be smoothed out because of this range of compositions in the particle.
Thank you. Yeah, that's helpful.
Okay, so this is a very famous graph from Atlum's paper. I think it's really awesome. And what it does is it shows you the fractional capacity that you can expect from a particle of either a spherical, cylindrical, or plane shape as a function of Q, all right? So when Q equals 1, remember this is when the time that you're taking to add lithium to the particle is the same as its characteristic diffusion time. The graphs that I calculated were for plane particles, okay? And at Q equals 1, sure enough, we got about 63% of the full capacity at Q equals 1, just like this graph predicts. But look what happens for a sphere at Q equals 1. You get almost over 90%. And this is because the sphere promotes this three-dimensional diffusion into the center. So you end up being much more effective with spheres than plane-shaped particles. And with spheres, for example, if you go at Q equals 0.1, so that means only giving the thing a tenth of the time, tenth of the characteristic diffusion time. For spheres, you still get about half. But for plane particles, you get less than 10%. So this graph was really one of the first times people realized the advantage that spherical shaped particles brought to the table compared to infinite cylinders and slab type particles. A sphere of the same radius and diffusion constant gives you a big advantage over a slab of the same radius and diffusion constant. So any questions about this? Okay, I don't hear any. All right, so, well, there's no reason with enough mathematics that you can't do this completely right. So there's people that do full cell physics-based modeling of cells. And John Newman's retired now. Jan Reimers was really good at this when he worked at E1 Moly. He had some fantastic software. Bob Spotness worked for a company called Battery Design Limited, and now he works at Enovix. So he's out of this game. Ralph White is a professor at University of South Carolina, and one of his students, I think Ray Smith at Tesla worked with Ralph as an undergrad, and then he went off to MIT and worked with Martin Bazant, who's also one of these big modelers. And then Professor Wang at Penn State formed a company called EC Power, where they make commercial software that you can purchase to do these full calculations. And what these do is they model the concentration of the lithium ions within the electrolyte in the separator, in the pores of the cathode, in the pores of the negative. They also model the lithium concentration as a function of position within the electrode particles. So they're really nice pieces of software. And to do this absolutely perfectly, you have to understand that the diffusion constant of lithium depends on the temperature, not only in the cathode and anode particles, but in the electrolyte. And this particular paper that Valowen and Reimers wrote explores the difference in these first principles physics-based models of cells, where you assume diffusion constants are constant as the cell discharges, or you realize that as the temperature of the cell heats up, the diffusion constants improve. So let's try to figure out what's going on here, okay? So this is for a LiMn2O4 graphite lithium-ion cell. So it's a spinel lithium-ion cell. And what he was trying to do is calculate what the capacity versus the voltage versus capacity curve would look like under conditions of a fairly large discharge current. I don't remember what it was. But anyway, there's a lot of these dash curves that you see here, which predict a small capacity. And in this case, he was using a fixed diffusion constant, you can see. To model the full lithium-ion cell, which is one of these data sets over here, he used what he calls full properties, which are a diffusion constant that depends on temperature. And then he was able to model things quite well. And if you want to know why that makes such a difference, over here, he's showing you the lithium PF6 concentration in the electrolyte as a function of position in the electrode stack, starting at the anode current collector over here at the left and going to the cathode current collector over at the right. So this is a discharge. So it means that the lithium ions are coming out of the graphite and going over to the cathode. So the gradient has to be from anode side to cathode side. And you can see what happens here. So this is 2 amp hours into the discharge. I forget what capacity these were. But you can see that when he assumed a constant lithium ion diffusion in the cathode particles, in the electrolyte, that the concentration of the salt in the electrolyte went to 0 at a portion of the cathode. So that's here at the 2 amp hour point, which means that you're going to be unable to fill these particles at the back of the electrode with lithium, and you're going to get reduced capacity, which is what happened. But then when he used a diffusion constant that depended on concentration and temperature, then you get this other profile, and the concentration does not go to 0 at the back of the cathode anymore, and you are able to model the full capacity of the cell. Okay, so this, you know, this work began because they're trying to model these cells, and once the discharge currents became large and the cells started to self-heat, couldn't model them anymore. And the only way to do it is to know how the diffusion constant of lithium in the electrolyte depends on concentration and temperature. And I showed you their data earlier on in this particular PowerPoint, back when we were talking about properties of electrolytes. Okay, so any questions about this? So our baby model about the limiting current in the electrolyte, we would assume a straight line from, you know, the max concentration to 0 across the electrode. And it will be interesting to see, you know, how close to the max current that we would predict with our simple model this current that he's actually selected is. It's going to be pretty close, right? Because he's gone almost from twice the equilibrium concentration down to 0, right? So he should be very near the limiting current that we would predicted for that electrolyte from our simple baby model earlier on. Okay, any questions about this? So here's a paper by Tom Fuller. He's now at University of Central Florida, is he? Or is it Georgia Tech? Can't remember. And Mark Doyle went to work at DuPont. He may still be there. And John Newman's retired, I think. But this is a very similar type of calculation, again, for a graphite LiMn204 cell, where they're running the thing at 4 milliamps per centimeter squared, and then taking a look at these electrolyte concentration versus position in the cell at different times during the discharge. So at 0 minutes, the concentration's even everywhere. 8 minutes in, 18 minutes in, and 65 minutes in, you can see they've driven the electrolyte concentration to 0 at the back of the cathode side. And this is a graph, a calculated graph of the energy density of the cell as a function of the power that it's delivering. So this could be C rate on the horizontal axis and capacity on the vertical axis. So it's like a Ragone plot. In fact, it is a Ragone plot. And what they're showing you is what happens as you change the thickness of the positive electrode. You correspondingly would change the thickness of the negative according to the cell spreadsheet model that we developed in class. So you can see that when the electrodes are thin, you can get a lot of power before it drops off. And when the electrodes are thicker, you get more energy density, but you can deliver less power, okay? So these are the kind of things we all know from our experience, but you can calculate these things relatively easy with these physics-based models. So in previous years of the class, I have purchased a 4-seat license to this software called AutoLion, which comes from Professor Wong at Penn State. And this allows you to do these full cell calculations. And everybody would come into our laboratory and sit at our computers, the 4 that had this software on it, and do a lot of calculations to really explore the impact of particle size, porosity, electrode conductivity, temperature, charge and discharge rate, all these things on the voltage versus capacity curves of cells. And I think students really enjoyed it. But I figured since we couldn't all come into the building, I didn't know how to do this. A 4-seat site license for this thing is about $4,000 US. So I didn't do this year. So you're not going to learn how to use AutoLion. I can just tell you it's a very nice piece of software and very useful. So I apologize, but COVID is what it is. Okay, I think that's the next slide. Okay, so we're done this particular part, and we're going to start on the safety part now. Before we move over, does anybody have any questions on this? Okay, I think you'll get a good appreciation for many aspects of this when you do homework 6. Okay. So I'm going to share my next PowerPoint with you. Obviously, we won't get, okay, can you see this new PowerPoint?
Yes.
Yep.
We won't get too far into this because we only have 10 minutes to go, but really I want to talk to you about my thoughts about the safety of lithium-ion batteries, you know, and why they have a safety-related problem at the fundamental level. You know, and it's important because electric vehicles sometimes do catch on fire, and it can be really bad. But I must tell you that over the last, you know, actually all the way since 1991 till now, the safety of lithium-ion cells has dramatically improved. Just to give you a feeling, when we had our issues at E1 Moly Energy with lithium metal, molybdenum disulfide cells, we put 2 million cells into the field, and we had 10 safety incidents. Okay, that's 1 in 200,000 cells. How do you detect that at the experimental level? You think about it. Not easy to do, 1 in 200,000. At that time, we figured the safety had to be one incident in 200 million cells. So 1,000 times better to be able to make a viable business where you could handle the lawsuits and so on that were coming back at you. So with lithium metal in liquid electrolyte, the ability to make a viable business, I would say, is, you know, unless a miracle occurs somehow, due to Alex Luley and Ahmed and Michael and others working in this anode-free space, it's pretty limited. If you think about EVs and the safety of lithium-ion cells now, it's incredibly different. You know, it's probably one incident in several billion cells, and maybe even lower. And the main contributors to that are, you know, precision manufacturing, the separators that are ceramic coatings on them, better electrolytes, and so on and so on. but we really need to understand, you know, where the issues are coming from. Now, just to put everything on the right page, and I'm not saying, you know, this is the way people should compare things, but you have to realize that there's a lot of fires that take place with gasoline-powered cars. So here, for example, in this document, each year from 2014 to 2016, an estimated 171,500 highway vehicle fires occurred in the United States with gasoline cars. Okay. Annual average of 345 deaths, blah, blah, blah. 13% of fires responded by fire departments across the nation were these car fires. You know, and I had no idea that things were this bad with gasoline-powered cars. And I think it was about 3 or 4 years ago. Actually, it was just about when I started working with the Tesla guys. You know, at that point, there were incidences with Model S's, and even with the incidents that were happening, it was still something like a factor of 20 less likely to have a EV-related fire compared to a gas car-related fire. And now the Tesla Model 3 and the Y, the safety is way better in those than the S. So EVs are getting way better and better all the time. Okay, anybody want to make any comments about this?
Jeff, there's much less fire for the electric vehicle, but the energy density of this lithium-ion battery is much lower than gasoline. So yeah, that's just one comment.
Yeah, well, that's true, but a gasoline tank can't have an internal short circuit. Okay. All right, so we're going to start off this discussion by just considering the fact that, you know, many compounds or mixtures of compounds are not in their thermodynamic equilibrium state. So what's in a lithium-ion cell is not in its thermodynamic equilibrium state. And as an example, you know, you could take a mixture of hydrogen and oxygen. You could mix them together in a gas cylinder or into a balloon, and nothing would happen. They would prefer to be water. But they're stable for a long time unless they're heated. And it's because there's an activation barrier in the way. So you have hydrogen plus half an oxygen that wants to become water. And for that to happen, you move along a graph where you look at the energy of the system as a function of reaction coordinate. It's going to move to lower free energy, but to get there, it has to move over an activation barrier. And this is the Arrhenius treatment of exponentially activated reactions. You say the reaction rate depends on some frequency factor, which represents how these molecules are interacting and how many times they attempt to cross over this barrier per unit time. And then a probability factor, which is with what probability will they actually make it over this barrier. And that's e to the minus EA over KT, so this is called a Boltzmann factor. And this EA is the activation energy, or the height of this barrier that I've shown in this graph. And eventually, if you heat things enough, you know, this temperature gets really large, this term becomes very small, and the rate gets larger and larger the higher the temperature is. And this is the whole problem with any kind of mixture of things that aren't in their lowest free energy state. They will try to go there as you increase the temperature. And I want to give you an example. I think I should stop here because this example takes a bit of time, and it's very important to understand this example very well. Yeah, so I'm going to stop here. So are there any questions about this very simple thing? Okay, I hear none. All right, so we'll be back on the air on Wednesday, normal time. I've given you another homework 5, right, to work on. And I'll wait a bit before I give you homework 6. Don't want to have too many at the same time. All right, see you. Bye.